Hi, hi Fiona, this is Ross Garton here. Starting my project with um, an object moves in a straight line at a constant speed from the point 1 minus 13 when t is equal to 0 to the point 11, 17, 6 seconds later. To describe this 2D movement, we first need to get the slope of the line. We can get this when we have 2 points and we use our slope formula. So we put in y2 minus y1 over x2 minus x1 for our 2 points and we find the slope of 3. We next find the equation of the line. To do this, we need to find the value for c. We then pick one of the points in the line and put it into our equation. So we can see that c is equal to minus 16, and now we have our equation of the line y is equal to 3x minus 16. So our next step is to build in time. We can see that the movement is from 1 to 11 in the positive direction in 10 seconds. So that's 10 over 6. So that's 5.5 divided by 3 units per second. So t is equal to 5 over 3. So we need to replace x by directed speed, but multiplied by time plus initial position. The next step. So we have our equation of the line. L of x here now is x and 3x minus 16. Where necessary, we need to delay the start time to t minus delay, but it's not necessary for this question. So we build in time into this equation, and so we've got 5 divided by 3 times t plus 1 for x, and then we put 3 times 5 or 3 times t plus 1 minus 16 into the other. So we're replacing x here by 5 over 3 times t plus 1. So we get 5 over 3 times t plus 1 and 5 over t times minus 13 as our equation. So we can now evaluate this when t is equal to 0. Our point on the line is 1 minus 13. When t is equal to 6, our point on the line is 117. So that proves that we have the right formula. As we can see here, the points match, and that's the equation described. In our next question, we have an object initially located at point 76. It takes 90 seconds to complete a circular motion of radius 7 about our center point of 0.6. So I have the solution here. I have it done. First, before I got it completed, I firstly put in the equation a sine t, bt plus c, and a cosine t, bt plus c. So that was our initial starting point. So the first thing I looked at was to get the center point of 0.6. And to do this, I added 6 to the yt and left x at its default 0, because that's where the 0, so that left the center point at 0.6. I noticed that when I had the circle completed, it only did a quarter motion, a perfect quarter from here to here, so I increased it by 4 times t, that made it a full perfect circle. To get the radius of 7, I multiplied cosine and sine by 7. We have an accurate circle shape and not have it oval. We had 7 and 7. See, I changed the sine and cosine order to get the point from 7, 6. I think it initially was starting over here somewhere. So when I changed cosine around, it started at the right point that we wanted. But it also made it move in an anti-clockwise direction, which didn't matter, we're still moving in a circular motion. So our final equation here would be for xt 7 times cosine 4 times t, and yt would be 7 times sine 4 times t plus 6. And that's our final equation. Okay, to create a straight line motion, we have a straight line movement as the x and y values are moving at the same intervals. So we have x going up and y going up at the same intervals, and there's no powers. That creates straight line motion. Okay, to create wave motion, we need to have a trig movement in one axis and movement in the other axis. So we can see that it causes, in this it causes a wave motion negative in the y-axis. For example, if we don't have movement in one of the axes and we have trigonomic movement in the other, we get a bounce, whereby we have a wave motion, but it just bounces from side to side, and we don't really see the movement at all. It's just moving over and back here. So we have a constant value in y, and if we really wanted to see that wave, we need to be increasing that y as we go down. So to create circular motion, we need to have sine and cosine working together at the same speed. So here we've got our sine radians and cosine radians the same speed, and we get a circular motion. Now, for example, I'll go down to here, and here we have sine working at 3 times speed and 2 times the speed, and we get a closed curve as a result. We don't get our perfect circle. So in circular motion, if we want to control the radius, here for example we have 5 times sine t and 5 times cosine t, but that result did increase the radius on the x axis to 5 and increased it on the y. As we increased them both at the same value, we got a perfect circle. We increased our sine and cosine. For example, if we didn't increase sine and cosine at the same value, like here, where we increased it by 2 times cosine and 4 times sine, we ended up getting an ellipse circle. So it's not a perfect circle, it's like a kind of oval shape. So if we want to control the center point of the circle, we can add values at the end of our equation. See, we have cosine radians here -3 and +2. So the -3 and +2 in effect have changed the center point to the point -3 on the x and 2 on the y. So that's our center point here. So that in effect controls where we want to locate our circle. To control the speed, we have increased t by 2 in the examples, and that is a result of the circle really going around twice. And I just highlighted here. As you can see, I've gone from 0 to 170, nearly half the way, and you can see that it's already done full motion. So if I would write down to all my values and points, I would have gone around the circle twice. So to control the starting point of my motion, whereby if I had sine here instead of cosine, the point would have been 0.13 I would have started at. When I changed cosine here instead of sine and sine here, my starting point would end up being 7.6. So that was the one way I controlled it. And that also changed direction. So instead of going clockwise, when I changed cosine to the x position, it moved in a counterclockwise motion. So some of the things I might have covered in this. Yeah, just an example there of moving 3 times sine and 3 times cosine. I have some waves there. You can see that if we're looking at how it affects the amplitude, it affects the radius in the circle by 3 in each, but it also affects the amplitude in the waves by 3. Just an example. And I think that's all. Thank you.